Hello students, this is Mr. McAllen, and today we're going to do some problems to demonstrate the following. We're going to use polynomial theory to explain graphs of polynomials, their extrema, end behavior, and zeros. We're going to try describing end behavior using limit statements. That's going to be a new thing that you may not have done before. We're going to find zeros of polynomials algebraically. We're going to look at multiplicity of roots and what does that look like when we graph functions. And we're going to graph polynomial functions if given the roots of a polynomial function. So, in our first example, it says to use a grapher to plot f of x and then use polynomial theory to explain the extrema, the zeros, and the end behavior. So we're going to plot this on Desmos to see what it looks like. X cubed plus 2x squared minus 11x minus 12. So x cubed minus plus 2x squared minus 11x plus 12. Let me just check to make sure that's right. That would be minus 12. And as you can see, we have our graph, but we really should zoom in to make sure we're not missing any behavior here around 0. So I'm going to zoom in to make sure that we have no crossings of the x-axis. And look, we do have some crossings. Those would be called zeros. So you can see here we have a 0 at -4, we have a 0 at -1, and we have a 0 at 3. So I'm gonna plot those on my graph. I have a 0 at -4, a 0 at -1. So I have a 0 at -4, a 0 at -1, and a 0 at, I think it was at 3. And I know the function has this type of shape because it's a third degree polynomial. And when you know any third degree polynomial has a general shape where the end behavior, basically a regular x cubed polynomial, the end behavior always comes in from underneath and it leaves, actually there's like a, this is a shorthand way of writing a cubic function's end behavior, or like x cubed's end behavior diagram would look like that. It would look like a parabola with squiggles in the middle. Anyhow, if we want to explain the extrema, how do we know we have two extrema? We know that at maximum we have two extrema because it's always whatever the degree of the polynomial is, it's always one less. So whatever, if the degree is 3, then 3 minus 2, 3 minus 1 tells us that we're going to have two turns in the function. So here we have a turn from it's going up to going down, and here we have another turn. And where the function turns is where you have extreme values. How many zeros do we have? You always have a maximum number of zeros the same as the degree of the polynomial. So I can't have more than 3 zeros. That comes out of the fundamental theorem of algebra, or 3 solutions. So what about my end behavior? The end behavior model is characterized by the highest degree of the polynomial. So here my end behavior model looks like x cubed. Now in one of the objectives we said we were going to discuss end behavior using limits. So here's how we describe that end behavior. So if you have a function that as x approaches infinity, the function value approaches infinity, then you would write it like this. The limit as x approaches, you write lim for limit, as x approaches infinity of the function equals infinity. This is the y value of the graph. This is the x value. Now for this limit here, as this goes off to negative infinity, you would say the limit as x heads to negative infinity of the function is going to equal negative infinity, because as x goes to negative infinity, the function value f of x heads to negative infinity. So that's what that limit statement says. So that's, we're going to do that again on the next problem just to re-emphasize the limit notation. So now we have a really big polynomial here, but basically this polynomial, we can learn everything we need to know about it just from the leading term. Because it's a fourth degree, we know that its end behavior model will look like this, where it comes on both sides, it is heading upwards on both ends. So how many zeros does it have? Maximum 4. How many extrema? It has a maximum of 3. It has a maximum of 3 because you take the fourth degree, 4 minus 1, tells you you have a max number of extrema, max of 3 extreme values. That means you could have less than 3 extreme values, but you're going to have a maximum of 3. So if we were to graph this and use polynomial theory, well, polynomial theory is basically like how we come up with those ideas on the zeros and the max and the extrema. If I were to graph that in Desmos, this is going to be tough for me to remember. So I got 2x to the fourth plus 2x cubed. That's not too bad. 2x to the fourth plus 2x cubed let's go back to the function, minus 22x squared minus 18x plus 35. I can now see that my function does look like a W in terms of it does resemble even polynomial behavior, where on both ends it's heading upward. Now, when I look for my zeros, I see that I have a 0 at negative 3 about. It's not quite, it's like negative 3.02. Let me make sure that my polynomial is right. So, and I have a 0 at about 2. I have a 0 here at like almost 1. Another 0 at 3.08. So let me just make sure that I didn't mess up copying this down. 2x to the fourth plus 2x cubed minus 22x squared. Okay. Minus 18x plus 35. Well, I have the function incorrectly, and you can see here that I have the right graph. So what I'm going to do is so I don't have to recopy this all, I'm going to just copy this graph from Desmos, and I'm going to put it in on my sheet here. So I'll delete that, and I'll just paste it in. And now we can talk about it more intelligently here in terms of what the end behavior is and everything. So if we were describing the end behavior as x goes to infinity, the function value is heading to infinity. So I'd write that up as a limit as x goes to infinity, f of x becomes infinity. When I look on the other side, as x heads to negative infinity, my function value, f of x, is heading to infinity. So you'd write that as limit as x goes to negative infinity, f of x heads to infinity. So there's my end behavior. Now, in terms of the number of max extrema, you can see here I have a low value, a high value, and a low value. I have 3 extrema, which comes from the fact that the degree of the polynomial is 4. So 4 means A degree of 4 means you have a maximum 3 extreme values. And when you have also fourth degree, it means that the end behavior is going to behave like a fourth degree polynomial, which just looks like this. So that helps you write up your limit statements. And then you also have a y-intercept of 35. So these things help you graph the function. If you can't solve the function or solve for the zeros, you can at least draw up a reasonable sketch. In the last part of this video, I want to talk about how we solve a function graph algebraically. So in this function right here, we're going to solve like we normally would in an algebraic sense. We're going to set x cubed minus x squared minus 6x equal to 0 and solve. What type of behavior is it going to have at the end? It's going to look just like x cubed. How many extrema is it going to have? It's going to have 2 extreme values, a high and a low. And we're going to be able to find all those values, or at least draw a reasonable graph. If I factor an x out first, I have x squared minus x minus 6. Now I factor the trinomial. This is working with algebra. And now I get my 3 zeros. By setting each linear term equal to 0, now I have x equals 0, x equals 3, and x equals negative 2. I'm going to plot my zeros. And I'm going to know because of my end behavior, the function is going to come up, dip down, and go off again. So that tells me or shows me how I can draw this function quickly when I solve it algebraically. Find the zeros algebraically, well, we did that through factoring. If I want to talk about end behavior or extreme values, properties from polynomials would help you explain that, or theory about polynomials. And we have one other thing to talk about, is what happens when you have repeated roots. So the idea of this example, what happens, so here's a question, what happens if we have repeated roots? Construct a function that has repeated roots. Okay, so here I have a function that has repeated roots. I have x equals negative 2 as 2 repeated roots. When you have even an even number of repeated roots, we have polynomial bouncing. When you have an odd number of roots, you have a through root. So odd roots, odd numbers of roots, or odd number multiplicity. Right? This means it's a through root, not a bounce root. So what you do is, we're going to say at x equals, we have at x equals 1 and x equals negative 2. Those are 2 locations for roots. But here we're going to have a through root. Here we're going to have a bouncing root. So I put b and t, so I know what that means. And then because overall this is x cubed, I can draw my root, or my polynomial, so it looks like x cubed. It approaches 0, but it bounces, and then it comes back, and it goes out just like the end behavior of an x cubed function. So this is an example of what you would do if you had repeated roots. So what would happen if this was squared and that was squared? Well, it would, let's draw that scenario. I would have bouncing, and then I would have bouncing again. But because it's 4th degree, it would come in from the top, it would bounce, and then it would bounce again. And it would look just like a W. So hopefully this video has helped you understand some of the basic things that happen with polynomials and their roots and limit statements. And we'll practice more of this in class.